Start sharing my screen. Okay, after the session ends, the Zoom session ends, we'll have a break 10 minutes because the Zoom doesn't let me get to the room within 10 minutes. So we'll do the same things as we did in the previous lecture. In the last week lecture, I had a trouble. I forgot to record the second lecture, I guess. So I have 2 lectures and I still didn't upload the lectures yet into YouTube and my YouTube account. You'll be able to access the lecture videos this evening. I will upload them, the previous week lecture and this week lecture also, and you also have the opportunity to download the lecture notes as the PDF file. All I write here will be on each week lecture notes, so you can download it, no problem. Okay, last week I'll get to the title, back to the title. Look, hypothesis testing for population mean when sigma is known. This week we will be dealing with when sigma is not known. So there is a trouble, notability. Yeah. Okay, look, I get back here. Hypothesis testing and confidence interval for population mean when sigma is known. Today, when sigma is not known, there are 2 ways. This is 10th of March. 2023. Okay. So B, hypothesis testing. And confidence interval for population mean. Sigma is sigma unknown. Unknown, and n is greater than 30. So there's another way we can tell. If sigma is not known, the population standard deviation is not known from previous information, then there could be 2 ways. Either n is greater than 30 or n is less than 30. If n is greater than 30, you use the same critical values from the Z, the Gaussian normal distribution table. So I'm going to copy the same hypothesis we construct here. So I'm going to copy this page, all this page, right here, from there up here. Copy. Yeah, right here. Gonna add some pages. Yeah, there you go. Yeah. Yeah. Okay. Okay. Okay, we also built the same hypothesis three hypotheses: left-tailed, left-sided, right-tailed, right-sided, or double-sided or two-tailed. The hypotheses are the same. The only difference is we changed the test statistics. The test statistics we're using the same way you calculate the statistics. The only difference is you change sigma is not known. In place of sigma, you have the sample standard deviation. So in place of sigma, we have the sample standard deviation. That's the difference. We change sigma as S, and then the sample standard deviation, you have learned it in the previous semester. I'll show you how you can perform calculation of the sample standard deviation. I'll try to move this bit down to use the space I need. I can also shift this down too. Okay, I'll shift this down a little bit more just to use the space for the calculation of the sample standard deviation. You have learned it in the previous semester. Remember, the sample standard deviation was S equals 1 divided by n minus 1 and time the summation xi minus x bar squared. This is within the square root. If you take a look at your lecture notes in the previous semester, you'll see this formula. Or in the examination, I don't mind how you get the result of the standard deviation. You can use a scientific calculator to calculate the sample standard deviation when a data set is given to you. So you only need to enter the data set directly into your calculator, and the calculator will present you with a shortcut, pressing 2 to 3 buttons, and you'll get automatically the output, the result of the sample standard deviation. So I assume that you have learned already how to calculate the sample standard deviation. Okay. The other thing is, of course, yes, it's the remaining is all true. The only things I could modify the sigma in the confidence interval, and I have to consider this as S, and this is S, the sample standard deviation. This is not given. The population standard deviation is not known, and you need to calculate the sample standard deviation from the sample. Let's have an example. So if you have read the lecture note in the previous week, so you will easily understand what I'm doing today. It's not that hard, it's really easy. Okay, let me have an example. I'm gonna copy an example from the book I'm following. The example, although in the example, the population standard deviation is given known, so I will assume that it's not known. We will assume it's not known. Let me show you the example from the book. Let me see. This one. Yeah, there you go. Number 14, I'm gonna copy it. Okay. I pass it right here. So there you go. That's the example. So I'm gonna just zoom it. Look, freshman GPAs, first semester GPAs for random selection of freshmen at a large university are shown below. estimate the true mean GPA of the freshman class with 99% confidence and assume. So I'm going to I'm going to delete this. Okay. So I'll add that here. Assume sigma is unknown. Okay. So, and adding to the question something else. Test that for alpha equals 0.01 level of significance, the null hypothesis, you write it down, the null hypothesis, the mean GPA is less than plus equal to 2.6, and the alternative mu is greater than 2.6. The mean GPA is greater than 2.6. That's the claim. The claim and the judgment will always be in the alternative hypothesis. Test that whether the mean GPA of the student, the freshman student, is greater than 2.6. So we don't have the X bar, we don't have the sample standard deviation. The sample standard, we were going to estimate the sample standard, the population standard deviation using the sample standard deviation. So in this exercise, in this example, let me get to the solution. Okay. So we know the X bar. We need to calculate the X bar. The sample standard deviation, we need to know the result of the sample standard deviation. I need to know what the sample size. I can easily determine the sample size by counting the number of the values given. 1, 2, 3, 4, 5, 6. In each group, I have 6. So I have here 1 and 2, 3, 4, 5, 6. 6 by 6 is 36. So the sample size is 36. Mu null is 2.6. And I also need to know the critical value. So this is a right-sided hypothesis. So I need to know what 0.99. So let me just write you this 1 minus alpha, that is Z, and the subscript will be 1 minus 0.01, that is 0.99. So I need to bring this value from the table, and that's it. I can easily manage the remaining. And I also need this value for the confidence interval, that 1 minus alpha divided by 2 for the confidence interval. This is 1 minus 0.01 divided by 2. And you can easily perform such calculation and see the result is 0.995. So I need to bring this value from the Gaussian distribution table. Okay, before I get the calculation of the X bar and the sample standard deviation, I will bring you the critical value for the hypothesis testing, and for 99% confidence interval, I'll bring you the critical value as well. So 0.99 So if I get to this Gaussian standard normal distribution table, Gaussian table, so you need to find out where 0.99 is located. So look, 0.99, this is the closest. You can approximate this value, 0.99, for the Z standard normal table. So look, here you have 2.3, 0.99, 2. So the result is 2.33. So you know how to determine this value from the previous semester already. And this is determined by table E. So I can easily write the result for this one. This is going to be 2.33. And the other one, look at this one, 4.995, 4.995. So I'll get to the same table. Need to find out where 4.99, 9960, 49, and 51. You see, it's very close. So it's between this value and this one, 0.9950. So it's 2.5, 7, and 8. 2.57 plus 2.58. So in the central of those two values. So I can easily write this down, the critical value, as this is between 2.57 and 2.58. So the middle of those two value, and the result is 2.575. So that's the result of this critical value of 0.995. So I'm also liking the result of X bar and the sample standard deviation. So to calculate this, you need to use a scientific calculator, or you can use a computer. Of course, if the examination is going to be face-to-face, and you will bring your own calculator. But if you're taking the examination from distance, you can use a computer to perform such calculation easily, much easier, and with no error. You will not make any mistake from the computer. So I'm using Excel. I prefer to use Excel. I have 36 values. So I'm going to enter column B, the observation value in Excel in a column. I can use Excel as a calculator for me. It's much easier for me because I'm not only, I have forgotten to share my video screen. I'm so sorry. I haven't seen that my camera was off. Okay. So the first value, look, 1.9. I'm going to enter all the data values. 2.8, 2.5, 3.1, 2, 2.1, 3.2, 3, 2.7, 2.7, 2.8, 2.4, 2, 3.8, 2.8, 3.5, 1.9, 3. Oh, the next column, 2.9, 2.9, 2.7, 3.2, 3.8, 4, 3.4, 2.7, 2, 3, 3.9, 2.2, 2.9, 3.3, 1.9, 3.8, 2.7, 2.8, and 2.1. Okay, 36 value I already entered. So I can easily tell the mean. I can calculate the sample mean. mean, standard deviation. In Excel, I can perform it easily. I have the functions, available functions for this. So once you are in the selected cell, you click on this automatic plumb, or if you're using an English version, it will tell you automatic sum. I click on the main and the selected area, it will present me. So I'm going to just have 4 digits, so diminish the number of digits. Okay, 2.8194. Yeah, and the standard deviation, I can easily write a function for the standard deviation. If you're using a Turkish version, so this would be the standard sapma, STD sapma. Dot S is telling you this is for a sample standard deviation. If you select the previous one, dot P, it will be the population standard deviation. So we are dealing with a sample. So I have to select this function. So, and then I will select the data set I'm dealing with. So I'll select all of it, and it will present me the sample standard deviation, which is 0.6159. Okay, I can easily write everything I need. Okay. So if I get this, yeah. So I have the result. We'll bring it here. Right there. Fine. So look, this is the value. That's the result. That's the result I'm dealing with. Okay. So the mean X bar is 2.8194. The sample standard deviation is 0.6159. Okay. Yeah. Okay, I did perform such calculation, and I know what the statistics, the Z statistic, the calculated statistics is X bar minus mu null divided by the sample standard deviation divided this is by the square root of the sample size. So I can easily get this done. The X bar is 2.8194 minus 2.6 divided. The sample standard deviation is 4.6159. That's divided by the square root of 36. Okay, in the beginning, you may feel that the mean GPA is greater than 2.6. You see, this 2.81 is greater than 2.6. But if you conclude that is true, this is the claim, the judgment is true, it is greater than 2.6, the mean GPA, that will be incorrect because this is not statistically correct. This is from a sample. We don't know yet. We have to check whether this is true. Let's see whether this is true. Okay, get this done. If you get this done, I'll try to do it right here in Excel. Okay. So I'll write a function for the Z statistics within a bracket 2.8194 minus 2.6, and I'm dividing this by 0.6159. That's divided by 6 also. Let me see. I need to place a bracket here, entire bracket, braces. Okay, 2.1374, the T statistic, the Z statistic, the calculated Z statistics. So this is the calculated statistics, which is, so I can easily write it down here. It's the result is 2.1374. That's the result. Okay, the calculated statistics is 2.1374. Then from this value, I can easily tell whether the null hypothesis is rejected or not. So I'm going to place the Gaussian distribution, graphical display of the Gaussian distribution. Yeah, it is. Okay. Can I use this picture? So since this is a right-sided, we know whether the hypothesis is right-sided from the alternative hypothesis. If it's greater, so it's going to be right-sided. I will replace the side, the critical value on the right side. Okay, so it will be somewhere here, probably. Okay, so this is, okay, so this is the reject region. So this is 0.01 level of significance, and that's the accept region. This is 0.99. So I'm going to highlight this area. So that's the critical region. Okay. Okay. The calculated statistics, and we need to determine the critical value. The critical value we determined already is 2.33. So this is 2.33, the critical value, and the calculated statistics. Okay, the calculated statistic is simply falling within the accept region because it's smaller. So I will have a line here, somewhere here, perhaps. Okay, it's 2.1374. Okay. Okay, since 2.1374 is less than, is not greater than, let's say not greater than 2.33 or 2.1374 is falling outside the reject region. Area. The null hypothesis is not rejected with alpha 0.01 level of significance. Okay, so that's our conclusion. But when you look at the mean of those students, the GPA is less than 2.6, greater than 2.6, but there is no evidence to support the idea. There's no such evidence that to support that this is really the mean GPA is greater than 2.6, even if the sample mean is much greater than 2.6, but this is not statistically significant. Okay, we do not tell that this is significant, so it's insignificant. So there is no evidence to support that the mean GPA is greater than 2.6 with 0.01 level of significance. Okay. The Zoom session will end probably in 5 to 10 minutes. Then after 10 minutes, we will have a break at another 10 minutes before I get to the second lecture. Okay. So the confidence interval, to construct the confidence interval, remember the confidence interval was X bar, confidence interval, X bar minus Z1 minus alpha divided by 2 times the sample standard deviation divided by the square root of the sample size, less equal mu, less equal, and the X bar plus, this time I'm having a plus, 1 minus alpha divided by 2 times S divided by the square root of N. So it's easily performed. We know the critical value. We have done it. We have found it already, 0.995, which is 2.575. There you go. That's it. It is. Okay. And then substitute everything I need. The X bar is 2.8194. It's already there on the screen. This is 2.8194 minus 2.575. And the sample standard deviation is 0.6159. And this is divided by the square root of 36. The square root of 36 plus equal mu plus equal 2.8194 plus 2.575 times 0.6159 is divided by the square root of 36. Okay, so I'm going to use a calculator. It will not take me much time. Okay, 2.8194 minus 2.575 times 0.6159 divided by 6. The result is the lower bound is 2.555 and 1. Let's equal mu plus equal, and the upper bound is 3.0837. So that's the confidence interval. Okay. All right, so that's the confidence interval, and you can tell that to interpret the confidence interval, we can tell that the mean GPAs of that large university with a confidence level of 99%, it is between 2.5551 and 3.0837. It should be between those two values. So this is the lower limit, the lower bound, and that's the upper bound of the confidence interval. So let me interpret this, write the equation. The mean GPA of that large university is between 2.5551 and 3.0837 with a 99% confidence level. So, of course, it means you collect the sample 3,600 times. If you have 100 times of 36 sample sizes samples, each sample, 99 of those samples will be within the interval 2.55 and 3.08, and one of the samples might be outside the range of 2.55 and 3.08. So that's the interpretation of the confidence interval.